All right, new recording. So I'll get you back my whiteboard in just a second if you're finished copying, but the next thing that I want to do is find the Laplace transform for this new unit step function with the step at a. So that's going to be my next thing that I want to do. We want to repeat the process that we just did. We're going to do it with an integral, and we want to find the Laplace transform for this new unit step function. So let's go back to the whiteboard and see what happens there. So if a is less than or equal to 0, then the Laplace transform of this unit step function is just 1 over s again. And again, this is for s bigger than 0 or s bigger than or equal to 0 either way. The same thing is going to happen if a is less than or equal to 0. You're just going to get an integral from 0 to infinity of 1, and then you get the same thing that you did before. So if a is less than or equal to, this is boring, by the way. This doesn't come up very often. And the reason that this doesn't come up very often, especially in differential equations, is because usually t represents time. And so it doesn't make sense to have negative time. So this is fine from a mathematical standpoint. From a differential equation standpoint, it's probably not going to show up in practice very often because time is not going to be negative. So let's look at what happens if a is bigger than 0. So if a is bigger than 0, then we want the Laplace transform of the unit step function at a. And again, remember, since I don't have a place on the board to go back to, let's write down the definition here. Remember, my unit step function is 0 if t is less than or equal to, I think just less than a, and 1 if t is bigger than or equal to a. Okay, so limit with an integral. Limit as b goes to infinity, integral from 0 to b, e to the negative st times this unit step function, and then dt. Okay. This time, we're going to have to split this integral into 2 separate pieces. So we're going to have limit as b goes to infinity, integral from 0 to a of something, and then the limit as b goes to infinity, integral from a to b of something. The function changes rules at a, so therefore I need 2 separate integrals because I've got 2 separate rules for the function at a. First one is going to give me e to the negative st, and then if I'm between 0 and a, my function value is 0. So I've got 0 dt. If I'm between 0 and a, the value of my unit step function is 0. If I'm between a and b, I still have an e to the negative st, and then my function value is 1, and I've got a dt. So I need to split my integral into 2 separate pieces, one from 0 to a and one from a to b. This first piece is really, really handy and just goes to 0. It totally goes away because I've got a 0 inside of my integral. So that first one absolutely positively just goes away. The second one is what we have to evaluate. And we kind of did this yesterday or Tuesday. So antiderivative, I still have a limit out in front. Limit as b goes to infinity. Antiderivative negative 1 over s, e to the negative st. And this is now evaluated from t equals a to t equals b. If you don't remember that antiderivative, go back and look at my notes from Tuesday, or go back and look at class from Tuesday if you're not sure where that antiderivative is coming from, or write out your u substitution, however you want to do it. But we got negative 1 over s, e to the negative st, and then we need to plug in our values. So limit as b goes to infinity, negative 1 over s, e to the negative s times b, minus negative 1 over s, e to the negative s times a. So I'm plugging in my values with my definite integral. Limit as b goes to infinity, negative 1 over s e to the negative sb minus negative 1 over s e to the negative sa. I've got two minuses, so we can go ahead and make those into pluses. So two minuses will make me a plus. This second part here does not have any b's in it, right? So nothing is going to happen to that second part as b goes to infinity. That's just going to stay. First part, we need to look at the exponent. We did this on Tuesday, but we did it really fast on Tuesday, so we're going to do it again. So let's look at the exponent for that first part. We're going to kind of throw this off to the side of the screen, and then we will come back and evaluate that limit. So as b goes to infinity, I want to know what happens to negative sb. And there's going to be two cases. One is if s is negative, and one is if s is positive. So if s is negative, then this part right here, there's a negative out in front, there's another negative, and then there's a positive, right? One more time. If s is negative, there's a negative out in front, there's a negative right here, and then there's a positive. So this is going to go to positive infinity. If s is positive, there's a negative out in front, there's a negative right here, and then, sorry. If s is positive, there's a negative out in front, there's a positive here, and there's a positive here. So negative sb is going to go to negative infinity. Depends on whether s is positive or whether s is negative. So look at the signs of what you're multiplying together. Negative, negative, positive, so positive infinity. Negative, positive, positive, so negative infinity. If my exponent goes to positive infinity, this thing diverges. If my exponent goes to negative infinity, then the e part is going to go to 0, right? Think about the graph of e to the x. So this is going to go to 0 if s is bigger than or equal to 0. Think about your graph. Think about what this looks like. This is going to go to 0 if s is bigger than or equal to 0. So this limit ends up equaling 1 over s e to the negative sa if s is bigger than 0. If you want to make it into a single fraction, you can say e to the negative sa over s. And again, this is if s is bigger than 0. So there's my Laplace transform for the unit step function with a step at a. Here's what we just did. I lost my pen, sorry. We just did the Laplace transform of the unit step function with the step at a is e to the negative s times a over s, and my domain again is s bigger than 0. So this is what we just did with the Laplace transform the long way. I can't back stuff very well in drawing mode. If you look at the chart in the front of your book, that is totally going to match up with what is there. So if you have the chart in front of you, or if you can pull it up, the chart is going to match what we just did here. Stuart, question.
Yeah, so I guess I'm just confused because if negative SB is going to positive infinity for S is less than 0, how come we're not using that and like getting a second answer?
Right, so think about what happens. Let's look up in the corner over here. Let's see if we can do this. Oh, no, sorry. Eventually, I'll get very fluid at this whiteboard, although I don't want to. All right, so let's look at what happens. So I will have a second answer, kind of, sort of. I want to look at negative 1 over s e to the negative sb, and I want to look what happens if the exponent is going to positive infinity, right? Potential second answer there if the exponent is going to positive infinity. So think about the graph of e. What happens to e as you are going to the positive infinity with an exponent? What happens to that whole e? Thinking about the graph, this whole thing right here goes to infinity. Yeah, so this whole thing goes to infinity, positive or negative, I'm not sure really which, I don't care mine. And that means that the integral diverges, Remember that terminology
Got it.
way back from Calc 2, the integral diverges. So that's why we're not worrying, and we're saying that S has to be bigger than 0. If S is less than 0, I don't get an answer for my integral. Good question.
Okay, that makes a lot more sense.
Okay.
Thank you.
That's also how we get the domain for our Laplace transforms. If the values of S are going to cause the integral to diverge, we don't include those values of S in the domain for the Laplace transform, because we only want Laplace transforms where the domain is, or where the integral converges. All right, I'm going to pull you back together. I'm going to stop sharing my screen and see if other people have questions. Anything else? Other questions that came up through that example? I can see you all again, so you can either virtually raise your hand or you can really raise your hand. Any questions on that? Doing okay with the integral that we just evaluated? Yes, good, happy, give me a thumbs up. We're good, very good. Okay, one more thing for today, and I'm going